So welcome everybody, welcome to the people here in class, welcome to the people that are connected through Zoom, welcome to this open lecture of the Master of Philosophy here at USI in Lugano. Indeed, let me start by saying a few words about the program first. It is a 2-year master. It is taught completely in English. It is based here in Lugano, Switzerland. Among the requirements is a bachelor in philosophy, and it is also accessible as a second master. So students who already have a master in philosophy can enroll to take this one as a second master. And to tell in a few minutes the essence of the math, I thought of boiling it down in 4 numbers. The numbers are 87%, 4, 25, and 2000. People that were here last year maybe remember what these numbers refer to. Other people might try to guess. Right, let's start with 87%. So 87%, what is it? Well, the master is designed to prepare students for PhD applications and for PhD programs afterwards. And 87 is the percentage of graduates who wished to pursue a PhD and actually got into one. So 87% of our graduates who wanted to do a PhD since the very beginning of the program in 2017 have actually started one. This corresponds to roughly 77% of all the graduates. This is because the majority of our students actually want to pursue a PhD afterwards. You find a list of placements on our website, but these students have proceeded with PhDs in various PhD programs around the world, such as the University of Oxford, the University of Southern California, the Australian National University, and so on and so forth. This was the first number. The second one is 4. 4 are actually the 4 core areas of the master. So the map is not a generalist master that covers any area of philosophy, but rather is focused on 4 specific areas, which are metaphysics, logic, philosophy of mind, and philosophy of physics. And all the courses are actually organized around these 4 core areas. As you can see in the list of courses of this year, or now actually this next year, the mandatory courses on the left and the elective courses on the right. The third number is 25. 25 is actually the number of professors that teach in the master. I actually suspect that this year is more than 25. In any case, these are leading figures in the 4 core areas. So if you have started working in these areas, I'm sure that you have read some of their work. Not only they are, of course, interesting people to work with, but they also act as personal tutors for the students of the program. And these include people, I'm not gonna name names, I'm just gonna show photos. Here, I am sure you're going to recognize some of those photos. The fourth and last number is 2000. So 2000 is basically the semestral fee of the program. So maybe a little bit more than public universities in Europe, but definitely less than universities in the UK and the US. On top of the semestral fee, I would say that the students have several funding opportunities. Several of the students that are here are actually supported by scholarships, both private, but also the ones offered by the faculty itself, and by the possibility of actually serving as student assistants, a position that comes with, of course, duties that enrich your CV, but also with a salary that is not insignificant, I would say. In case you are interested in the program and would like to find out more, there is a website and an email address that are reasonably simple, I would say. We also are present on several social media platforms, including Facebook for the old ones like me, Instagram, X, and YouTube, where you find recordings basically of our talks and open lectures, including the one that we are about to attend. Speaking of which, I am actually introducing once again an open lecture by Øystein Linnebo, entitled Abstraction and Abstract Objects, which is effectively, I think, the first lecture of his course here at the master this year, because it's a few years that he is actually teaching in Lugano. I don't remember how many, maybe 4.
This is my 4th year.
4. In his course on philosophy of mathematics. So please, Øystein, the floor is yours.
All right, thank you. Yeah, so this is the first lecture of that course in philosophy of mathematics. And the topic this year is abstraction and abstract objects. So do you all have a copy of the handout? Good. Since I'm going to teach this in the old style, really, with whiteboard to illustrate a bit, and then referring to the handout quite a lot. Another thing I should say about the teaching is that I like to make things quite interactive. So we have a good amount of time here. And we'll first go until 5, I gather, with the recorded bit. And then we'll take a 15-minute break. And then we'll resume again and continue for an hour until 6:15. And that's a fair amount of time. So it means that there is an opportunity for you guys to stop me, tell me that something is hard, that you have questions, ask me to clarify. Maybe I use terms or use ideas that haven't been explained yet. So do stop me. I very much encourage that. Okay, and then we'll do most class practicalities tomorrow when it's not doubling up as an open lecture. So let me keep it to the absolutely minimum now. My email address, if anyone needs to get a hold of me, that's the easiest one, Linnebo, my surname @gmail. And then let's just get going. And topic then, as I said, abstraction. Yeah.
Sorry, will you set the...
Oh, okay, yeah. So we start here. Yeah, good.
And if you want to stop sharing the screen, since initial presentation.
Okay, so I click OK here and stop sharing. Yeah. Okay, sure. Good. So all set up in terms of technicalities then. Good. So yet again, abstraction and abstract objects. So concrete objects, you know what those are. So people are concrete, tables, chairs, stones, trees, right? Objects you can bump into. So that's the easy kind of objects, relatively speaking, the concrete. And we will be talking about the abstract, which roughly can be characterized as what is not in space and time, and what is perhaps for that reason not causally efficacious. So it doesn't enter into causal chains or causal interactions. That's not maybe a perfect characterization, but it's good enough to get going. Okay, so not spatial temporal and no causal. We may well talk about trickier cases, so maybe there are objects that are in time but not in space, like feelings, thoughts, psychological objects. So we'll talk about trickier cases, but very roughly to get going. we have a dichotomy between the concrete and the abstract being what's not in space and time. All right, and then I gave you examples of the concrete. What about examples of the abstract? There are lots. So I encourage you actually to just open a newspaper at some point and look at the nouns that you find in the newspaper and how many of those nouns refer to something abstract, or at least somewhat abstract. Right? So a democracy or a government or so they do have some concrete aspects, but there's a lot of relatively abstract stuff talked about all the time. But pure examples here would be numbers. Right? So we say both in mathematics and in totally ordinary talk that there are, I don't know, 45 people in this room, or the number of people in this room is 45. And another standard example would be sets. So collections. So we could look at the set of students registered here and the set of students who are just visiting the open lecture. Those sets do not overlap, so we talk about properties of these sets. So numbers and sets are really abstract objects that you encounter a lot in quite ordinary language. And then in mathematics, you go beyond that, and you have functions and spaces and all kinds of abstract things. Okay, so that's the topic. And why are we interested in this? Well, abstract objects are quite tricky philosophically. They're quite weird in many ways. So concrete objects, you feel you have a fairly good sense of what they are, like they're things, and you're familiar with them. Of course, there are all kinds of tricky philosophical questions about the concrete too. What is it for such objects to persist from one moment of time to another, or what changes can they undergo, all these things. But the abstract is much more puzzling. So I think a lot of people just find abstract objects puzzling right at the outset of how could there be these objects that are not spatiotemporal? Isn't that somehow even a requirement for being an object? So there's a kind of just metaphysical puzzlement concerning them. That's one thing. What I find more interesting than that is epistemological challenges to the abstract. And here I have in mind questions about how we can have knowledge of abstract objects. So think about how you have knowledge of ordinary physical objects. So why do you know there's a blue water bottle on the table here? Well, there's perception. You know how perception works, where the photons bouncing off the water bottle, hitting your eyes, triggering reactions in your brain, which result in the belief, the justified belief that there is that bottle. Right? So we have a sense, of course, again, lots of tough philosophical questions about the concrete too, but we have a sense, at least with the concrete, of how we have knowledge. But then look at truths about numbers or truths about sets. And then you ask, how do you know about those truths? What kind of mechanism is it? So there are these abstract objects, not in space and time. And you profess to have knowledge of them in some way. And there's no interaction that we can make sense of between the objects and you. Right? So when you have the ordinary objects like the bottle, and then you, there's an interaction that explains how you have knowledge. But when you have just 2 + 2 is 4, then no interaction that we can in any easy way make sense of. of course, through the history of philosophy, there's been speculation about various kinds of interaction between the abstract and our minds. So if you take our minds to be somehow quite, I don't know, detached from the physical and maybe independent of your physical body and so on, then maybe you make your mind more akin to, more like the abstract realm. But that's not very tempting these days. So our mental faculties have something to do with our bodies, no doubt. So it remains a mystery then how you can have knowledge of truths about abstract objects. Okay, so that's a mystery we will talk more about in, I think, the third lecture. I mention it now just to put on the agenda the kind of puzzlement and weirdness of abstract objects. Okay, so that's a starting point, that this is philosophically interesting. We talk about the abstract objects, and not only do we talk about it, but there's a whole very successful science of it, mathematics, which is way more successful than philosophy when it comes to making steady progress, and mathematics talks about these abstract objects. So it seems we've got to account for that in some way, philosophically. All right, that's a starting point. Any questions at that point already? Okay, so what I'm going to do next then is to lay out the main approaches to this postural problems that we will talk about in this course. So it will be a lot about abstraction, which is an operation that may well work on concrete objects and give you abstract objects. So I'm going to give you one example here, numbers. Okay, so if I ask you to consider all the people in this room, and then we could look at the number of all the people. Okay, so we have maybe some objects, these objects, and you have some other objects, those objects. Right, so these and those, maybe the people on this side of the room and that side of the room. And then I'm going to write this relation for being such that they can be put in one-to-one correspondence. Okay, so this is the relation of being matchable in a one-to-one manner. Okay, so if these are 3 crosses and those are 3 balls, then you can, of course, match these in a one-to-one manner, for instance, in that way. Many ways to do it. Okay? And then what's nice about this is that the objects that you consider may well be concrete objects. So relatively clear objects before anything abstract is entered. So they may well be concrete. And secondly, the relation here between the two pluralities, as I will say, of objects, the relation of one-to-one matchability, or I'm going to give it a name, equinumerosity. They are said to be equinumerous. That relation is something that one can also make sense of talking just about the concrete. Right? So when I say that my right-hand fingers are equinumerous with my left-hand fingers, that matchability can be made intelligible in a totally concrete way. Okay. And then the idea is that when you look at numbers, think about numbers, then numbers are somehow measures of how many collections are. So you look at some things and you ask, what about these objects? How many are they? Or what about those objects? How many are those? Okay. And then we're going to have that the number of these, I write sharp here for number of, is the same as the number of those. just in case, these can be put in one-to-one correspondence with those objects. Okay, so then we have a link, so to speak, between the concrete, possibly on the right-hand side, and the abstract, for sure, on the left-hand side, in the numbers. All right, so that link and that kind of abstraction move that takes you from the concrete to the abstract will be really the main topic here. And we call it abstraction because you kind of abstract away, you set aside some features of the entities that you start with. Right? So if you started with these 5 fingers or those 5 fingers, you ignore all aspects of the two things that collections that you abstract on, other than how many there are. So in this case, you really ignore a lot about the items that you abstract on. You preserve just how many there are or their number. All right, so so far so good. Do interrupt me. And then there'll be really four approaches to making sense of that kind of abstraction that we will discuss. So today the main topic will be a very old one of quantity and magnitude. Okay, so we're going to talk about the old ancient tradition, really. A lot of this found in Aristotle, of talking about quantities. So quantities could be, well, I'll go into detail soon, and their magnitudes. So how much a certain quantity is. And you could see these as quantities. These and those would be discrete quantities, and numbers as magnitudes. So that's one way of making sense of this. Another approach is nominalism, which is the philosophical view that there is actually nothing that is abstract. Everything is concrete. So you totally deny the existence of anything abstract. But one recognizes, of course, that it's in some sense correct to say that the number of people on the right-hand side of the room is identical with the number of people on the left-hand side of the room. In some sense, that is correct. But then the nominalist says that the left-hand side here of this principle is really just a kind of convenient shorthand for the right-hand side. So the right-hand side is what really is true, that really, does describe reality. The left-hand side is just a way we have of speaking, but you don't have to take it seriously. It's a kind of fiction that we talk as if there were these numbers, but really they aren't. And really all we mean to convey when we say these things is that. And as we'll look at in later sessions, that's actually a super efficient way to talk. So when it comes to actually making sense of basic arithmetical features of concrete objects, it's so effective to have ordinary arithmetic. So we pretend that you have the things on the left-hand side. You do operations on these pretend numbers to get them information about the good old concrete objects, which is all you believe in. So that's nominalism. That's one, and then we'll go on to talk about Fregean, the great German philosopher and logician. and his way of thinking about abstraction. So what Frege does is to also operate with this principle, but he understands it a bit differently from the old Aristotelian tradition of quantity and magnitude. So he says that these really are objects, numbers are objects. That's like distinctive of the Fregean view. And he also insists that you can do all kinds of abstractions. So this is a huge generalization compared to the old theory of quantities and magnitudes. So some examples here, just to give you the flavor of that, would be shapes, geometrical shapes, or types as opposed to tokens. So let me explain that. So you could have shapes in the sense of shapes that I draw on the board. And then you could talk about, you can have an equivalence on shapes too. Of, do they have the same shape? Right? And then, of course, the two triangles have the same shape. Triangle and circle do not. So then one can try to abstract shapes as what concrete figures have in common when they are formed in the same way. Okay, so you could generalize this kind of equation to also cover shapes. Or you could do the case of types as opposed to tokens. So this could be letter types, for instance, where there are 4 letter tokens, right? And 3 letter types. Since these are 2 tokens of the single letter type A. Okay, you could do the same thing, of course, with all kinds of things. So not just letters, but sentences, books. So we say things like, you and I bought the same book, or you and I read the same book. And in a sense, that's true. In a sense, it's wrong. So you have your copy, I have mine. So different tokens of the book, but it's the same type of book. Okay, so the type token distinction is pervasive. And the Fregean tradition here tries to get types into this sort of abstractionist format and see the types as something we can account for by abstracting all the tokens. And the very last approach, which we'll look at, is structuralism. And that very name indicates quite a lot about the view, that it's a view that emphasizes structure, and how structure is what matters. So here, what you abstract on are not just individual things like letter tokens or book tokens or something like that, nor is it pluralities of things that you have made sense of already. Rather, what you abstract on here is a whole system of things in certain relations. So that could be, I don't know, 3 balls ordered by increasing size, or you could have triangles ordered by decreasing size. So there's a sense in which you have 2 systems of objects and relations that are structured in the same way here, right? There's 3 objects standing in a relation, with 1 first in the relation, 1 second, and 1 final in that relation. And the objects that stand in the relation are different, and indeed the relations are different too. Since the first relation is increasing size, the second relation is decreasing size. or it could be mass, or it could be age or people. Maybe that would have been a better example. But you get the point. Okay, so what structuralism is interested in is structured systems of things and what they have in common when they, in this intuitive sense that I just illustrated, instantiate the same structure. There's a fancy word for that, namely isomorphism, which we will talk about. Some of you will know. And of course, those of you who know your Greek will know already, since morphic is form, iso is same, so they have the same form, right? So there's a sense in which these two systems of objects and relations have the same form. They are isomorphic. So then the equivalence relation we are interested in that case is isomorphism. And then you study abstract structures. So the structure that these two systems have in common. So that's yet another huge generalization, where you generalize more than even Frege did. So one could hold on to everything Frege did, but get yet more, because you study whole systems, not just individual things. Okay, so the plan is to in lectures 1 and 2, talk about quantity and magnitude. Lecture 3, we'll talk about nominalism. Then there'll be 4 through 6 on Frege cell abstraction, and the final 2 lectures on structuralism. So that's where we're going to go. And then let me end this little introduction with some things to look out for on topics that I will be interested in here. So you have these 4 approaches, and they tend to be described as really very different philosophical views. Often they're seen as competitors, and you know how philosophers are, that people like to have their views and then try to argue against other views. But I'm also interested in ways in which there's some grain of truth to many of these views, of how they needn't necessarily be competitors. Of course, there are many things they do disagree about, but also a similar topic, namely operations of abstraction, like the passage from in this box from the right-hand side to the left-hand side. That's abstraction. They're all studying these operations of abstraction, and in that way saying something about abstract objects, or denying the existence of abstract objects in the case of nominalism. So some ways to compare the views then would be objects or properties. So let me explain. So take the example in the box with numbers, and then you ask, what are numbers? And then the old idea that numbers are magnitudes would have numbers be more property-like, right? So the number 5 is a property of these objects, these figures, right? They have the property of being 5 in number. So on the old Aristotelian tradition, the abstract objects, or at least numbers, are property-like. And Frege, by contrast, insisted that they are objects. So we're going to look at how deep that disagreement is. That's going to come up today already. Right, and here's the disagreement with the nominalist. Do you have objects at all? Or maybe properties for that matter, or not? other numbers, whether objects or properties, or are there no such things at all? So that's one contrast. Then another area of disagreement will be over the generality of the account, right? Where I said already that the Fregean approach that talks about shapes and all kinds of types that can be exemplified by tokens, that's way more general than the tradition of talking about quantity and magnitude. So generality, how general should the account be? That's an area of disagreement. And then lastly, should this be done for single objects, kind of one object at a time, or whole systems of objects? So that's structuralism versus not, where the earlier approaches said that, look, you get individual abstract objects like numbers one by one, as it were, by abstraction. But the structuralist says that no, you may as well start with a whole system of objects in complicated relations. Abstract on that, you get a whole system of abstract objects, a whole abstract structure. So those are the areas of disagreement to watch. Yes.
It's a very good question. Are systems supposed to be in the first order quantifier? They just seem to be instances of this. If they seem to just be instances of the abstraction.
Yeah, not quite, since there are all. So by system I mean some objects, but also the relations.
Yeah.
So they're not unless you take the relations to be in the range of first order quantifiers, then the systems are not. So a system would be kind of A related in one way to B, related in the same way again to C. So a bit more. That's good. Yes.
I have a question on the second point of nominalism.
Yeah.
Because in that principle, like conditional,
Yeah.
you are just referring to numbers.
Yeah.
You are then considering nominalism in an extreme way. So it's a lot of both numbers and sets.
Yes. Yeah. Now, so we're really doing both. So the nominalist does comment on the box here and says that the number talk is apparent only. It doesn't have to be taken seriously. Right? But the nominalist will go on and take that view not only about numbers, but about sets and about everything abstract. So most nominalists are not nominalists just about numbers, but about everything. It would be quite unusual to have a kind of selective kind of nominalism now. I haven't come across that. Sure. Good to get some questions here. So anyone else? Including just clarificatory questions or questions about where this is headed or... Yes.
Just really quick. So we have an equivalence that when we're doing abstraction, we have an equivalence, but I haven't found, like, for example, in that case where the operation can be found, like
in which case?
Like, for example, in that one.
In this one.
Yeah, like where's the operation?
Oh, the operation is this one, the number of operation. Yeah. So in all you're introducing a bit of terminology here. So let me pick up on that. So you have equivalence relations on the right-hand side. Equivalences, and we'll talk more about equivalences very soon. So in all these abstraction principles, as are known, you start with an equivalence, typically an equivalence that can be a hold between more accessible objects, like physical or concrete objects, And then there's some abstraction operation, in this case, a number of operations that you apply to abstract away many of the specific features, including then abstract away spatiotemporal location to arrive at something abstract. Right, so we're starting to get a little bit of an explanation even of why numbers are not spatiotemporally located. Since 5 can be realized here, and it can be realized there. Right, so the number 5 is no more located here than there. Right, so location is not preserved in the passage from some things like these things to their number. So then one says that location is one of the properties that you abstract away from. And in that way, one arrives at these, at the outset, rather puzzling abstract objects. So we're, let's see.
For the principles we have the early blocks.
Yeah.
Is it possible to have it without having the equivalence on one, like on one side and the limit on the other one? The case is just like these.
Yeah.
If you want to leave.
Yeah.
Like the real
Yeah.
number these.
Yeah. So to not have an equivalence here.
Yeah. And not even the other one.
Yeah.
Just have these and number these.
Okay, that's a big question. So let me write that up, and we're gonna look equivalence. We're gonna look out for that when we go into a little bit more detail. So the answer is that it's quite poorly behaved if it's not an equivalence. So you pretty much need it to be an equivalence, but I'll try to explain why shortly. And one more question here. Yeah.
You are having here the passage from concrete objects to number.
Yes.
But there is a bicondition. So
Yeah. So here
there's no abstraction.
What is?
It's
Yeah.
inverse of abstraction. This phenomenon.
Oh, all right. Yeah. Okay. So so this is abstraction, and what is the left to right? Yeah. That doesn't really have a good name, but instantiation, maybe, yeah. So concretization is a word I'm just making up right now. But, instantiation, yeah. So you're interested in 5, and then you want to, you're interested in 5 and its properties, and then you instantiate it in the concrete, and you study corresponding properties of the concrete to find out features of 5. Right? So if you're really bad at mathematics and you wonder whether 5 is divisible by 2, you may say that, oh, here's 5, and let me try how to divide into 2 equal bunches. Then no, it doesn't work. So answer is no. So instantiation is the best I can think of for the left to right.
Platonic.
Now, the Platonic view is very much that the left-hand side lives its own life and is independent of the right-hand side. So there's more of an Aristotelian element to what we're doing now, in that you start with what can be more concrete and you move to the abstract. So the abstract is explained in terms of the concrete, and that's a very Aristotelian explanatory direction. The Platonic direction now will be really to try to make sense of the left-hand side more in its own right, and if anything, use that to then explain features of the concrete. All right. Anyone else on the somewhat longer introductory remarks than I had planned? Yes.
If you want,
Yeah.
there's also a question in the chat.
There's a question in the chat. Yeah. Okay. So let's see if I pull that up. Okay. Greetings. Wondering if you could consider such a principle of abstraction to be genuinely logical. Okay, so are abstraction principles like these ones genuinely logical? Frege thought so. So here too, I think I'm gonna reserve the right to say that this is a topic that will be discussed more fully later on. Not on Zoom, alas, but so let me just say a tiny bit. Frege thought that an abstraction principle like this one is logical. That's quite a minority view at this point for a very simple reason, which is that you get objects here, and indeed you get many distinct objects in this way. And these days we have the view that logic does not have ontological commitments, other than maybe just one object existing to make logic work smoothly, and even that commitment could easily be gotten rid of. So the standard view nowadays is that logic should hold in any situation whatsoever, even situations with no objects. Right? So because of the generality of logic, you don't want logic to have any kind of ontological commitments. And that means that the principle in the box cannot be seen as logical, unlike what Frege thought. All right, so let me now turn to the handout then. And I trust people both on Zoom and you guys in the room here have the handout. So, right, and when it comes to assigned readings, do everyone have access to the readings here? And they've been made available, so that's fine now. Okay, so Keith Horsack is the author I assigned, who has then quite nicely recently now tried to revive an Aristotelian approach. So that's quite exciting with the number one approach here that goes all the way back to Aristotle, that Horsack has done a very nice job reviving. And we start with quantities. And quantities could be like pluralities of people, or look at other kinds of quantities soon. And quantities have two kinds of structure. They have a part-whole structure, or what's known as a mereological structure, and they support a notion of equality. So as much of some quantity as some other quantity. And then magnitude is what's shared then by equivalent quantities. That is the absolutely miniature version of the Aristotelian view. So then one sees these pluralities as quantities. I said already that they're discrete quantities. And then you have the equivalence on these quantities, right? Namely, the equivalence of being as many as. And then when two quantities, these and those, are equivalent, then they have a property in common, namely a certain magnitude, which in the finger case is a magnitude 5. So that's the structure of the Aristotelian account. And then nice features of that view is that it's very unificatory. It's a unified framework for many different kinds of numbers and quantities and magnitudes. And also it's quite explanatory in that the numbers and magnitudes here are obtained from something concrete. So when you started with this puzzlement that I mentioned at the outset about the abstract, so how can we have epistemic access to the abstract? And isn't that weird, all these abstract objects? Then you get explanations there, or so it seems, in that the magnitudes you obtain are instantiated in the concrete, and they're obviously relevant to the concrete, since the magnitudes are just properties of the concrete, right? So there's no mystery about why 5, the abstract number 5, matters to the concrete, since it's a property of these things and also of those things, and many other things. And one could study that property at a very general level. Okay, so that's the mini intro to Hossack. So what I was planning to do now is to go into more detail on the two kinds of structure that you have on quantities. So that we have, first of all, this neurological or part-whole structure. So there's a nice quote that you find in Aristotle that Hossack mentions, that quantity, according to Aristotle, means that which is divisible into two or more constituent parts. Okay, so quantities have parts, there are wholes that have parts. So quantities have a neurological structure. And then, as Hossack lays it out, there are three kinds of quantities. You have pluralities. And pluralities are really just bunches of ordinary things. So my finger example, or the person example, or something like that. Right, so pluralities. And then you have continua. Which are continuous quantities. And then lastly, there are what he calls series, which are some things in an order. So let me give you some examples here to make things a little bit more comprehensible. So suppose you're baking a cake, and then all kinds of quantities enter into that process of baking the cake. So you have a plurality of eggs that enter into the cake. And then you have some amount of milk, some amount of flour, some amount of butter maybe, right? And then the butter, you don't talk about one or two butters or one or two milks. You can talk about one or two packages of butter, of course, that's fine. But butter is just a continuous quantity, right? So you have some butter and parts of that butter, and likewise with milk and the flour, or at least the way we ordinarily think of it. So water, now you guys are sophisticated and know that water has minimal parts, namely water molecules. But set that aside and treat water as a continuous quantity. Okay? If that bugs you, that you need to pretend in the case of water, then look at lengths, right? So a length of an interval, that's a continuum. And then lastly, series are objects in a certain order. So a good example here would be a queue. So a queue of people, and where you could say that the queue of Alice and Beth is part of the queue of Alice, Beth, and Cassie. Example from the handout. All right, so I hope that makes sense, that you can talk about these different families of quantities. And they have important structure in common, especially the two better understood ones. So they have in common a structure known as classical, extensional, mereology. And mereology is just the study of a part-whole structure. And then extensional means that it's very extensional. Yeah, I'll give you examples of that later. Classical is that it's the most obvious part-whole structure here. Okay, and Hossack, following Aristotle, amazingly, has one way of characterizing this theory, CEM, of classical extensional mereology. And he does it in, let's see, so what if I take this, make myself some extra. So following Aristotle, Hossack has a fusion operation, which we write in this way, or addition operation. And then he defines a bunch of principles that should govern that operation. Or let me first give you the definitions, actually. So follow the order on the handout here. So using the addition operation, you can characterize part of it. So the property of X being a part of Y, we can characterize using just this addition operation. And that would be if you take X and add it to Y, you get Y back again. So the picture you should have here is that here's X, there's Y. So if you take Y, add X, you're not getting anything extra since X is part of Y. Okay, so I hope that makes sense that that is a good way to characterize parenthood, starting with addition or fusion. And then we go through a series of definitions that many of you will have seen before, but I guess not everyone, so I'm gonna do it. Where there's a notion of X being a proper part of Y, and that is that X is a part of Y, but the other relation does not hold. So X is part of Y, and it is not the case that Y is part of X. Okay, so this picture actually illustrates also X being a proper part of Y, since there's some part of Y that extends beyond X, as you can see. The next relation we need is that of overlap. So X overlaps Y if they have a common part. Okay, so that would be then that there's some Z, such as Z is part of X and also Z of Y. Okay. So the picture here would be that here's X, there's Y, and they overlap. So they have this colored part in common, right? The part in the middle. And the opposite of overlap is to be disjoint. So that they do not overlap. And this would be this kind of picture, that they don't have any part in common. They do not overlap. They are disjoint. Okay. So using just this addition operation, then Hossack, following Aristotle, we get to characterize all the mereological relations. Okay, so that's something to make sure you're on top of, and play around with that a little bit if you're not familiar with it already, to just prepare for tomorrow's lecture. It's good to just have this stuff at your fingertips. Any questions about these definitions or anything I've done so far? No? No. All right. So, I see yet one final definition on page 2. So upper bound and least upper bound. So if you have a whole collection of quantities, And then an upper bound would be something that contains all of them, right? So the outer circle is an upper bound since every one of them is a part of the outer one. And then the least upper bound would be the smallest thing that contains all of them. And that would be the object here that's enclosed by the thicker black line. So that's the least upper bound. I'm going to spare you the precise logical definitions. It's a very simple idea. And then, yes.
Just a clarification, is the operation of the composition here binary or can say
it's binary.
It's binary.
Yeah. But you're asking something very important. Yeah, so it's very natural to generalize this and allow the addition operation to really add up any number of things. That is a very, very natural way to generalize. And we will look at that too, I'm pretty sure, in later sessions. Yeah. Okay. So it's a little bit surprising, by the way, that I think probably the most technical, logic-y part of the course here is that which treats the oldest philosophical approach. So that's interesting. That it's really the Aristotelian ideas that call for the most formulas when you write them out. Of course, he described it just in prose, but it is kind of a nice observation. And then, let's see, it would have been so nice to have some more space here, but I don't. So I will make room here. What we're going to do now is to give the axioms for classical extensional mereology using this fusion operation or addition operation. And it's pretty simple. I don't have to write them down, all of them actually. So closure is that one can always apply this addition operation. It's always well defined to take something and something else and add them together. And that makes sense, right? If I've got one lump of butter and another lump of butter, you can consider the two lumps of butter together. Likewise with flour or the discrete eggs or whatever. Or even the cubes, right? So if you've got one cube followed by another cube, you could string the two cubes together and add the two cubes, as it were. Okay, so that's principle number one. Principle number two is something added to itself does not want anything new, unsurprising. Then you have commutation. So x added y is the same as y added x. And then associative law would be that the order in which you add doesn't matter. So maybe you add first two items and then a third, or you add the second and the third and then the first. It doesn't matter. Okay, so that's kind of how addition ought to work, but also how adding lumps of butter or quantities of flour works too. Right? It doesn't matter which order you proceed in. And then we have number 5, which is remainder, which I'm going to illustrate just. So this is that if x is part of y, you can consider that part of y, which is disjoint from or does not overlap x. So the remainder of y vis-a-vis x, what goes beyond x? So that's like a subtraction operation. In a sense, this is asking to consider y minus x. It's a kind of subtraction, right? Which is defined when x is a part of a proper part indeed of y. And then overlap, there's a characterization of what it takes to overlap a sum, which you could study. Then there's two quite strong principles at the end. So universe says that there is one universal quantity. So a quantity that has every other quantity as a part. So that would be the quantity that you obtain by fusing everything there is into one mega object of that contains everything that is a whole universe. So Hossack assumes that. We're going to see later that that's a little bit tricky, and it's not so obvious he should be assuming that, but he does. And then yet stronger than that is that you can not only take the sum of everything there is, but you can take any kind of sum. And I think this speaks to the question we had of whether the summing operation is binary or not. So the least upper bound, the eighth principle, in a way tells you that you can sum in an arbitrary way too. So if you have at least one object that is phi, then there is a sense in which you can consider all the phi objects and sum them all together. And what is that sense? Well, you could form the least upper bound of all the phi's. And so if these are the individual phi's, then you sum all of them and you get the least thing that contains all of them. Okay, so that's the theory that Hossack gives us of Aristotle on quantities, and it's quite nice that this is a theory that describes both pluralities and the continua. It does not describe series fully. Series are more complicated, and I left that as a question, a slightly hard question on the handout to try to formulate some mereological laws for series too. But classical extensional mereology holds for pluralities and for continua. And those will be the main quantities that we consider. So without looking at the handout, I'm going to ask you if you can think of any further properties that hold on the plurality, say, and then we're going to look at continua too. So pluralities are observe, it seems, all the principles of classical extensional mereology, but anything else that could be said about pluralities? What's special about pluralities? They're discrete, so that means they come in units, yes.
To distinguish them from continuum,
Yeah.
there would have to be some additional thing about how they can't be infinite or something like that, how they can't be gunky maybe.
Yeah, can't be gunky is what I'm looking for, yeah. Aristotle would also add that they can't be infinite. We're going to get to that very soon. So both things you said are true, but second thing first, that they're not gunky. And by gunky, we mean that within any part, you find a yet smaller part. So kind of infinitely divisible, going down into smaller and smaller parts. So we intuitively think of water as gunky. So you have a liter of water, and you could divide it into 2 half liters, and divide each half liter into a quarter liter, and so on. Of course, we now know, as I said a couple of minutes ago, that there are water molecules and so on, but intuitively, water is gunky, and for sure the parts of an interval, parts with any extension at all, would be gunky, since you can take here and divide and divide and divide. So continua are gunky in the sense that any part has yet smaller parts. And pluralities, you said, are not gunky. So that means, if we just work it through, if gunky is the property of being such that within any part you find a smaller part, then it follows that pluralities are such that for any part there will be minimal parts. Okay, so for any quantity of x, for instance, there's a minimal part which is some egg, namely an individual egg. Yes.
What about density? It seems that would invade both. I don't know. Like I don't know where.
Density. So so between any two, you find a third. Not in the case of pluralities, no. So so you got one egg and you got two eggs, and there's nothing in between. That's still a collection of eggs. You could, of course, leave the category of eggs and look at egg stuff, where there's 1.5 eggs worth of egg stuff in between the 1 egg's worth of egg stuff and the 2 eggs worth, but not when you talk about eggs. So then nothing in between 1 egg and 2. So pluralities are what's known as atomistic, that there are mereological atoms, meaning minimal parts. Yes.
So I had a follow-up on this question. Like, I don't really understand why. I didn't get why the varieties need to be modeled with atomistic mereology. Like, because I had in mind something like denseness.
Okay,
like,
for pluralities too.
Like I mean, you cannot have dense plurality, but maybe you have gunky pluralities. I don't. Just if you can go back and say why we don't want to have.
Yeah. So when you look at the plurality of eggs, the idea is that there are 3 eggs, and then you just go to the minimal parts, which are the individual eggs, egg 1, egg 2, and egg 3, and you can go beyond that to yet smaller things, but then it's no longer an egg. So when it comes to eggs, then this is the smallest it gets. That's why. Yeah.
But you can have. I'm pretty sure you can have something that has denseness, but still atomicity.
Denseness and atomicity, not in the present sense. So atomicity for us means a minimal part. Yeah. So you got minimal, but so could you tell me more what you have in mind then? So minimal parts and
at least how it's defined by Barty.
okay.
But that might be like a.
Let's talk about it and so let's I'm going to write it up here and we'll see if we can talk about that in the break or in the second half. Yeah, no, could well be, but atomicity in the sense of the handout here is that there are minimal parts, which are known as the atoms, and then the pluralities are atomistic, and the continua are the opposite, they are gunky. And then, of course, by mixing, if you're allowed to mix a plurality and a continua, then it's neither atomistic nor gunky. It's a little bit of each. Okay, so a couple of questions here that I gave you. Question number 1: why is this such a good way to axiomatize classical extensional mereology with this addition operation? It's of course nice that it's the Aristotelian way, as Hossack observes. But what else could one say here when you contrast this way of axiomatizing mereology with a more familiar way that some of you at least will have come across? So that's something one might want to think about. And then there's a question about whether the universe assumption should be accepted. I'll return to that shortly. And then top of page 3, we just covered in what we talked about here. And then one historical question, number 3, of what did Aristotle say about series? So that's the less familiar, the less well understood kind of quantity. And question 4 is it's a little bit hard, but probably a fun one to think about, of laying down mereological principles for series too, and see what you can do there. And one last observation before I go on to say a bit about equality is that there are all kinds of generalizations available here. And why do I mention generalizations? Why am I so interested in that? Well, remember that theme I announced of how general the account of abstraction should be. With Frege and the Phrygians arguing that you should go more general than the Aristotelian tradition does. So it is interesting to kind of poke away at the Aristotelian tradition and ask how much you can generalize that in a way that's motivated kind of within that tradition. And 2 examples I mentioned on the handout here are so-called superpluralities. So I talked about ordinary pluralities, which are some things. A superplurality would be some things, but grouped into distinct subpluralities. So this is 3 pairs, for instance. So it probably makes sense to talk about that without talking about sets. Right? So you have a fancy dancing performance, and you say that there were 3 pairs of dancers, right? And you're not talking about sets, you're talking about pair 1 dancing, pair 2, and pair 3. And that would be a super plurality, since it's a plurality that's articulated into kind of into a plurality of distinct subpluralities. Or you could have pluralities with repetition, for that matter. So we could talk about, I don't know, some race, and I ask you who are the past 5 winners of the race. And the past 5 winners of the race could be A, B, C, and A. So A won it 3 times, right? So the past winners is given by a plurality with repetitions. So you could allow that too. So there are ways in which one can generalize quantity beyond what we find on the list here, which will be important as we go along now. Any questions at this point before we look at equality? Yes.
So could you just explain why you think universe should not be accepted, like Aristotle should not accept universe?
I will get to it very, very soon. Yeah. Maybe I should have refrained from mentioning that quite so early, but I'll get there. Yeah. Anyone else at this point? We'll take a break soon, I promise. It's late in the day, and let me just start on the topic of equality, and just so we get going on that before the break. And so quantities, as announced, have the 2 kinds of structure: the part-whole structure, the mereological structure, and there's equality on them. So according to Aristotle, the most distinctive mark of quantity is that equality and inequality are predicated of it. Okay, so this is very important, according to Aristotle. And then there are axioms characterizing equality. So number 1, quantities that are equal to the same quantity are equal to one another. Okay, so if somehow 1 lump of butter is equal in amount to another one, and a third lump is equal to that second one, then the first is equal to the third in amount, in quantity. And then you have number 2, which is that addition preserves equality, as it were, but with one restriction. So let me illustrate here. So if this is equal to that in quantity. And if this is, so maybe I'm going to write it this way, equal to that in quantity, then summing these two will yield something that's equal to the result of summing the two rectangular quantities. Okay. And the one restriction on this that we need to impose for this to actually work, can you see what that is? No overlap, right? So if this one had been, if instead of this it had been that one, then it would work. So one needs to assume that the two quantities that you this and that, which you add up, that they are non-overlapping or disjunct. Okay, so that means that equality is preserved under the addition. Two more properties here. Trichotomy is that two quantities are unequal, just in case the first is equal to a proper part of the second, or the second is equal to a proper part of the first. Okay, so if the round quantity is unequal to the rectangular one, then the round guy is equal to some part of the rectangular one, maybe this one. So that makes sense. And lastly, no quantity is equal to any of its proper parts. And this looks super natural and plausible, but in fact turns out to be quite a substantive assumption, as we'll discuss after the break. So so it's the idea that when you have a quantity here and a proper part of it, then the proper part cannot be equal to the whole. That seems very, very plausible, doesn't it? That it's a proper part after all. So how could it be equal to, there's something you left out. So there's less quantity in the colored, there's less of the colored quantity than all the quantity. Yes.
So I have a clarification on E3.
Yeah.
I don't understand why it's a proper part, because I may have like two quantities, and they are equal, but either the first is equal to the proper part of the second, or vice. I mean, this to be equal to the thing itself, so a part of it.
Yeah, but the idea is that two unequal quantities. So it's not any two quantities, it's two unequal ones where, yeah, there's some butter and there's more butter, right? So, yeah. And then some butter is equal to a sub part of the more butter. Yeah. So that's the idea. Okay, so we would have time for one or two quick questions, and then we'll take the break. Yes, please.
For free.
Yeah.
Wouldn't it be the case to have two quantities?
Yeah.
One is smaller than the other one.
Yeah.
But the bigger one has no proper parts.
Yeah.
So like extend simple.
Yeah.
I mean,
That wouldn't work in this case. Yeah. So but that's a good one. Yeah. So if you did have an extended simple, yeah. So here's a big extended simple with quite a lot of quantity in it. And this is, yeah. Yeah, so you couldn't handle extended simples in this setting. No. Oh, that's a good one. What would the Aristotelians say about that?
Well, I think if you have,
Yeah.
if you think about parts more closely to the number, like the extension of the quantities, as like you have more parts if the quantity is bigger.
Yeah,
Maybe get this in mind when,
that's very much what they have in mind.
so it makes
Yeah.
sense that the bigger one that like just.
Yeah, that's right. Yeah, so but you see what we're so what one of the lines I'm going to be pushing here is that there is a real need to generalize. That the actually two lines, that the line number one is that the old Aristotelian account is amazing how much they could do and how much they could explain by way of demystifying abstract objects, making sense of abstraction operations, all that. So big credit for everything they did do. But line number two, that there's intense pressure to generalize more. And maybe this would be one way in which one should generalize more. So I think we're getting that the interaction of the merological structure and the equality prohibits extended symbols behaving in that kind of way. So that's a top possible essay question, actually, of how would you take a broadly Aristotelian framework and modify it somehow to admit extended symbols? That's a tough one, but that's something one could look into. Any other